Good morning, everyone. My name is Alain Boga. This is Davindra, Pooran, and Cobos, and we have the pleasure of presenting to you the project we did over the past year, the solar-powered water filtration system. The problem we had that we faced was that the world has a surplus of people who do not have water, about 700 million to be exact. These people don't have access to clean drinking water, and the water that they do have access to is oftentimes contaminated or has particles that they probably don't want to ingest. To motivate us, we wanted to do this because a recent report from 2015 actually showed that this crisis was one of the leading one of the leading risks for collapse of a society as a measure of devastation. And so how did we want to go about trying to alleviate this problem? Well, we wanted to utilize a energy source that was clean and affordable and renewable, and that happened to be the solar-powered source that we utilize with the solar panel. We wanted to make a system that could filter water and provide this water to a household of 4 people. These people would use about 400 gallons a day. This is based on a household family of 4. And so we wanted to extract 70 gallons of water per hour. This would amount to about 6 hours of runtime per day, which is the average amount of sunlight that the area that we wanted to deploy this in had. That area would be Haiti, oftentimes, not often, but sometimes Haiti is struck with devastating problems, such as the 2010 earthquake, where left thousands dead and even more without proper infrastructure. And so this would be deployed there, and the battery that powered the system would run for as long as it had power. So even if we had extended periods of rainy days or overcast days, we could still run this system. As for the standards we wanted to use, we used 2 sets of standards mainly. One was the ISO 17613. That dealt with the pumps that we used. That pump was able to, it dealt with removing water from bore wells, and those bore wells could contain sand or other particulates that were suspended within the water. The filter was probably the most important part of the standards that we used, as that dealt with the drinking water, and that was the ANSI and the NSF 42 rated, and that was with the reduction / removal of chemicals or pathogens or chemicals within the water. We also had to keep in mind towards the global design aspect, because not every country has the amenities that the luxury we have in the United States. So we wanted to design this system to have a very low cost prototype. And because again, these countries, particularly Haiti, has low income areas that we wanted to deploy this in. So we can't realistically have a very expensive unit. In addition to that, we wanted to make it very easy to use. We had to place the burden of knowledge upon ourselves, the designers, because again, Haiti has one of the lowest literacy rates in the Western Hemisphere, so we can't reasonably expect a high level of technical expertise to run these systems. And not all cultures might be welcoming of the technology, so we had to keep that in mind also. As far as our design, it came in we designed it in 2 stages. The first part that we can see here on the left was the prototype stage with the entire system, as we can see here. Shown is the interior of the system with the filter, the charge controller, and battery, and on the exterior is the solar panel. The second part was the optimization of the pump. So we designed the system with the pump in mind, and with that pump we wanted to increase the efficiency of the impeller that came with it. So we removed the impeller, designed a new one, and wanted to have better throughput. And again, here are the components, the main components that we used within the system, particularly the filter and the charge controller shown here.
All right, thank you, William. So in order to create the impellers, we had to use an optimization method. And the optimization method that we used was the backward circular arc method. As you can see here, impeller 1 and 2 are heavily based off of the original impeller that was supplied with the pump. And impeller 1 had a ring on the top. Impeller 2 didn't have the ring. Impeller 3 had a lofted bearing surface. And the point of these was to ease the manufacturing process. We had to remove the original impeller and then reattach these 3D printed impellers on top of it. So moving on, you can see the table which we used to construct the impellers, and these are values incorporated into creating the backward circular arc curve, which were imparted onto impeller 1 and impeller 2. So now that we came up with their designs, we decided to select a material suitable for testing, as well as one for our final assembly. So here you can see that we applied a 10,000 RPM centrifugal force into each impeller. The point of this was to see whether or not the impeller would last during the testing of each iteration in the assembly. So the 10,000 RPM equates to 0 foot of head based on the pump. At 0 foot of head, we have 10,000 RPM, 9 feet, which is halfway of the maximum operational region of the pump. We have 5,800, and all the way at the top, 18 feet is 1,600 RPM. So these numbers are important, and we use them for our testing. Impeller 2, you can see here, in the middle region is missing the conical sections, so the replacement was a bit higher, but all the impellers last fine in the testing. And moving on, you can see impeller 3 here. So finally, we compiled the data from each simulation, and we came up with these numbers, which we confirmed that although impeller 2 endured the highest stress and displacement, it was still fine. So now that we confirmed that each impeller would last for the testing, we had to decide a material to use. Since we're using a 3D printer, the XYZ DaVinci 1.0 in particular, we had two options, either PLA filament or ABS filament. ABS was not only cheaper, but it had a higher breaking point, and it was harder as well. Moving along, you can see that we utilized SolidWorks 2013 to conduct all of our simulations as well as designing. And in SolidWorks 2013, PLA is not even a material option for testing, as it's now becoming more and more popular with 3D printing surfacing. So again, ABS is cheaper, and it's also available in SolidWorks 2013, so it eased our simulation procedure. So now that we decided which material and whether or not the impellers would last during the testing, we wanted to get a reference as to how our impellers are going to perform during the actual testing of each iteration at each different head. Like we tested all the way up to 18 feet for 2 feet increments. So close simulations were conducted for each impeller, a total of 9 altogether, 3 for each impeller, 1 for 1,600, 5,800, and 10,000 RPM. We use these values to get a good reference to see whether or not a certain impeller would be more efficient later on. So finally, we compiled the data here, and we saw that impeller 2 outperformed both the impellers, and the optimization methods proved effective, as later on we saw that impeller 2 heavily outperformed the other two, and it was more efficient in certain head lengths.
Okay, I'm going to go over some of the stuff that we did during the construction and the testing phase of the prototype. As you can see, here is pretty much the overview again. And on the right side, we show the component location. During the assembly of the prototype, we came out with some problems that needed to be corrected. For example, one of them was when we got the panel, we realized that the panel it was bigger than the actual casing. And another thing for testing, we needed to find out a way to actually attach the new impellers to the magnetic shaft for testing. Modification made to the casing. As I mentioned, the solar panel was bigger than the actual casing, so the idea from the beginning was to actually place the solar panel inside the casing so it can be protected better, but that didn't happen, and in order to fix this, we decided to relocate the panel to the top of the casing cover by creating a structure in where it was going to was going to hold the panel for movement, and also it was going to protect it. This is pretty much us making an adjustment to the casing, and on the right side we show the complete assembly, and we did it in such a way that we can be able to slide the panel in and slide it out. And at the same time, we provided a cover that can be protected for little stuff like rocks or stuff like that. And the modification made to the impeller shaft this part was required for us to do the testing of the new impeller. The problem that we were facing is that the actually impeller was manufactured in such a way that there was a magnet attached to it, and we needed this magnet to actually do the testing on the other impellers. So what we decided is in order to do the testing, we decided to actually cut the original impeller, remove the original impeller, and actually by using an epoxy putty, we were able to bond the new impeller to the magnetic shaft. At the beginning, we were concerned if the epoxy putty was going to hold for the testing, because if you think about it, the shaft was going to be spinning, and the impeller was going to be moving water, and in between there's a torsion going on. So, but it actually works. The epoxy actually holds. Some of the formula that we use for testing and evaluation relates to power, Ohm's law, conservation of mass, Bernoulli equation. We also use Reynolds number. By using those formula, we were able to find efficiency, the pump performance curve, the system curve, and for efficiency, we use this formula in which it relates to the overall efficiency by using voltage and amperage taken from the pump. And here's the data that we obtained from the original impeller, and we were able to find efficiency, volumetric flow rates, pressure, voltage, and current. All this testing was done to all the impellers that we did, and it was done at different head length. This is the performance curve for the stock impeller, and as you can see, the orange line, I want to say is the pump curve, where it actually shows the capacity of the pump, and the original impeller was able to pump fluid to around 18 feet. And the other two, it actually shows the system curve, which means that the friction encountered by the piping that we use, the one that we used for the testing was the blue line, and I want to show that we were able to actually move the line up by reducing the pipe diameter and creating more resistance. Again, this is the data that was obtained for impeller number 2. The reason why we're showing impeller number 2 because out of the 3 impellers that we designed, impeller number 2 was that did the best. Here we show the efficiency of all the 3 impellers and the original impeller. The original impeller best efficiency came to be around 21%, which is around 10 feet of head length. Again, the original impeller against the impeller number 2. And in the highlighted section, we showed that the impeller number 2 was actually outperformed the original impeller by 3 locations. The first one was a 2 head and 8 and also 12 head length.
So for our cost analysis for the prototype, we actually had set a goal for ourselves of under $1,000 for the entire project. For the prototype itself, the entire cost came to $448, with the majority of the cost being weighted upon the solar panel. When we look at the overall cost analysis, our total cost was about $150 more than the prototype, so it came to about $606, well beneath our goal of $1,000, and helped us to accomplish our affordable, cheap system. So, in conclusion, we had all the theoretical values that we calculated with regards to the new impellers outweighed the performance of the original impeller theoretically. The efficiency that we gained from the impellers, particularly impeller number 2, which had our best performance, did perform better at certain points, 3 points along the performance curve than the original impeller. We didn't get an across-the-board increase in efficiency, and we can attribute that to the fact that we used a 3D printing method to create these impellers. While it did save us quite a bit of money compared to a injection mold system, we did have to face such imperfections such as edges that were not as crisp as if we had used that plastic mold injection. As far as our original goal of 70 gallons per hour, we well exceeded that at head lengths that were beneath about 10 feet for all impellers. The goal was higher than the pump rate was higher than 70 gallons per hour. When you went beneath that, to about 2 head, maybe 4 head, the gallons per hour was well above that, 180 in some cases. And so we exceeded our goal. Any questions? Yes.
Now, is this project solar power filtration or impeller design improvements? Because I appreciate the design because that's a lot of engineering there, so I understand that it's a nice process to design an impeller and everything. I mean, it's pretty impressive. But there was very little in regards to the filtration system or solar power. Now, your testing process of how you got that flow rate, where are you going to get 70 gallons per hour in Haiti, for example?
We designed the system to be portable. So the system...
I'm thinking water source, you know.
Right. So we could take it down to the riverbank or the lake bed to pump this water. Or if there's, say they had collected water from rainwater, then we could use the system to pump out and filter that water.
All right, so basically you would need that for drinking water.
Correct.
So drinking 400 gallons a day, that's a lot of water.
Well, that number is based on a U.S., an American family of 4. And typically in underdeveloped countries, they use about a half that, so about 200 gallons, but we designed it for 400 gallons a day. So you can use anywhere up to that amount.
So how did you test the flow? Well, you got that, was that with just tap water from here?
No, we actually had large drums of water, of rainwater actually, that we collected. And we had an apparatus where we had 2-foot increments of PVC piping. As Alain showed, the piping was about a 1/4 of an inch. And every 2 feet, we would measure flow rate, amperage, voltage, all the necessary parameters, and increase it by 2 feet until the flow rate maxed out and we couldn't get any higher. And we did that for all 4 impellers.
And that was going through your filter and everything?
Yes.
I'm gonna walk down to the river with this wheelie down to the river. Is there a hose in there that you
Yeah,
can put
yes,
in the river? You did a great job on the impeller, but how the heck does the rest of this thing work?
Don't know if we can see this, but there's actually this is removable. The filter here is connected to the hose, and the hose connects to the pump, which is right here. And so the filter, or the pump runs in, you put the pump in the water, it's a submersible pump. The filter, or the water goes through the hose. It's about 20 feet of hose, so it doesn't have to be necessarily right next to the bank. It could be 5 feet away, 10 feet away. It runs through the filter, and then the filter has an output hose, and that goes into the reservoir of your choice.
Okay, and you can shut that on, because I'm coming down there with 5-gallon jugs.
Right, you can. It's totally user controlled.
Turn it on and off.
Mm-hmm. There's an on switch here. Yes, sir.
Yeah, I have a few questions. On the filtration side, I would be making an assumption that I've got sand in my water, I've got aggregate in my water. Is there anything in the way your system is designed to be able to compensate for that?
The strainer at the beginning was to filter out larger.
Where's the strainer?
It goes here. We don't have it on here right now, but there's actually a strainer that keeps it from large rocks and stuff, because if we get any of the large rocks or twigs or anything in there, it would damage the impeller. As far as the sand, that was the standard that we used, and we searched for a pump that would fit that standard to filter out, to be able to remove the water while there is still sand in that water.
Okay, and now all of a sudden the sand went through your pump and it went into your filter. How do you handle that situation?
Well, the filter is meant to be replaceable. There are actually replaceable filters in here, and they're meant to be replaced every 10,000 gallons, so every 25.
If I'm pulling sand, and let's say there's 20% sand in my solution, how long is it going to take to clog up that filter?
Probably shorter, but a lot shorter of a time. But these filters are replaceable and very inexpensive. So even the idea is to not get too much sand in the system, to just put it beneath the surface of the water where there's not many
Okay, so the
particulates.
suggestion here is design in a backflow.
Yes.
So you got the ability to, like you have in your swimming pool today,
Oh,
for example.
push it out.
Okay. Solar panel size.
Yes.
Is that, did you calculate and determine the appropriate panel size to run this pump?
To run the pump, this pump run on 12 voltage and 2 amperage at maximum. So that becomes on 48 watts. And this panel is able to produce 50 watts at maximum sunlight.
At maximum sunlight?
Yeah, so if we don't have the battery in such a case, we can connect the panel straight to the pump, and the pump can run from the solar panel by itself.
But the way our system is set up is the panel doesn't actually directly run the pump. It charges the battery, and the battery by way of a charge controller, and the pump runs off the.
So you could have used a smaller panel?
Not really. Well, depends. If we use
It fits in the box.
Yeah, exactly. If the reason why we choose on 50 watts on a panel is because we actually did the calculation for the pump, and it come out to around 48 watts. So if we get a smaller panel, we wasn't going to be able to run it straight from the solar panel. So that's why we decided to go with the 50 watts.
If in a worst case scenario, if we had to directly hook the panel up to the.
And then we realized that the panel was oversized because of the thickness. We didn't account for the thickness of the casing. That's why it was
Okay. And is that filter a pathogen filter?
Yes, sir.
1 micron.